Assalamu alaikum. Today we'll be going over chapter 4.1 and some part of it, which is the central processing unit. And the first part we begin this chapter by is the von Neumann model. So, if you have ever researched about older computers, right? So, those were very big computers with a lot of tubes and a lot of wires around them, right? And when you go back in history, you seem to find out that those big computers were only able to perform one task. And if they had to do some other task, the wiring had to be changed totally, right? You could not retain the older task, right? So at that time, this model was presented, which would contain a central processing unit, a processor which would be able to access the memory directly, and the computer memories that could store programs as well as the data which was performed by the program. And stored programs were made up of instructions that could be executed in a sequential order, like one by one by one, and before losing everything, right? And this is a picture related to how the computer model looks right now. And it contains of a control unit, arithmetic and logic unit, some other registers, CIR, MDR, MAR, PC, address bus, control bus, data bus. So these are all the things that we are going to study in this chapter, and we'll go slowly, and there'll be multiple videos with all of the content covering all of these things you read here in this diagram. So let's move on to components of the CPU. So as you just saw, control unit, arithmetic and logic unit, right? So we're going to go over them. So first is the arithmetic logic unit. So as you can see from the name, it performs calculations and stuff, right? But apart from calculations, another thing that is very important is logic operations, right? So let us assume that in okay, so in chapter 3 you learned the AND gate, right? So AND is only true if we make the truth table for this, right? So AND is only true when both the things are true. So for example, if a computer is performing AND on to A and B, right? So unless they're both one, the result won't be one. So this calculation is actually being done in the arithmetic logic unit, and the accumulator is the temporary register used when carrying out the ALU operations, right? So you need somewhere to store all the data for the calculation to begin with. So that is where the accumulator comes in, right? Okay, now we move on to control unit. So the control unit reads instructions from the memory. The instructions are then interpreted. So when you read instructions, they won't directly make sense to the computer, right? You need to interpret them, and then using this process, there are signals that are generated to tell the other components their jobs, right? So let us assume that we have a task which needs to be done. Our new instruction is that we need to add two numbers, right? So the control unit needs to tell the arithmetic logic unit and the accumulator that this is their job, right? So you need to send out signals. And the control unit also ensures that the synchronization of data flow and program instructions throughout the computer. So if you have like readied up the accumulator and the arithmetic logic unit and you don't send the data on time, it can cause crashing in the computer, right? So you need the control unit to synchronize in order to perform data at its peak time, right? So you can perform the calculation instantly and you don't face a delay or a crash. And then we have the system clock, right? So we just read that we need to ensure synchronization of data flow and program instructions throughout the computer. So you need to time them, right? So we have the system clock that times the signals and then tells on the control bus to ensure that the synchronization takes place. So these two, control unit and system clock, work together to ensure the synchronization for a task to be carried out, right? Now we move on to immediate access store. So immediate access storage is basically your RAM, the RAM that is installed in the computer. And if you're watching this video after chapter 3, so as we have already read, the CPU cannot directly access secondary storage devices like the hard drive or the SSD, right? So it can only access the computer cache or the RAM, right? So the IAS or the RAM holds all the data and the programs that the CPU needs to access immediately, right? IAS is also known as the RAM, as we just I just told you, and the CPU can directly access this RAM, and the RAM is considerably faster than the secondary storage, right? So you previously what you do is, if you have a task and you require some storage from the secondary storage, so you take that the data out of the secondary storage and import it into the RAM. Therefore, when your CPU tries to access it, it will access the RAM directly, and the RAM is much faster, right? And it gives the data to the CPU in a much faster way. So that is how IES works, right? And the CPU works along with it. Now we move on to registers. So a register is a temporary storage area which is built into a CPU. Registers can be special purpose or general purpose. We're gonna read up on them a later bit in later videos. Okay, so now we're gonna go over the registers that are mentioned in our syllabus 9618. Okay, so we have the current instruction register, which is also known as the CIR. And what it does is that it stores the current instruction that is being decoded and executed, right? So the current instruction, as you can see by its name itself, so it works upon the current instruction, stores data about the current instruction that is being processed upon, right? Now we move on to index registers. So it is used when carrying out index addressing operations in the assembly language. If you move on to the next part of this chapter, right, so you'll face the index register and the accumulator a lot more, and in a lot more detail, because you have to dry run those programs and you have to perform trace tables. So you're going to get much more information related to the index registers later on. Then we have the memory address register. So the memory address register, MAR, stores the address of the memory, address of the memory location currently being read from or written to. So you basically know the address where you have to take the data from or write the data to. So that the address that is to be worked upon is stored in the memory address register. Now we move on to memory data register. So so you know the address where you have to write the data. So where is the data to begin with? So the data is in the memory data register. So it stores the data which has just been read from the memory, or data which is just about to be written to the memory, right? So these two work hand in hand. One knows the address, one knows the data. So you need the address to store the data, you need the address to get the data. So that is how they work together. Now we have the program counter. So program counter stores the address where the next instruction to be read can be found, right? So this is a cycle, right? You'll read upon this. We'll discuss the fetch execute cycle later on. So all these registers work together and the cycle continues, right? So once your current instruction is being done and it's decoded, right, so you move on to the next instruction. So the program counter is where the address of the next instruction is stored, right? And lastly, we have the status register, and it contains bit which can be set or cleared according to the operation. So let us assume you want to open a bit, right? So you'll read upon this in later on in bit manipulation, like you AND it to turn the bit off, you do this to retain the content of the bit. So this is all going to be discussed later on. So this was an introduction and the starting to chapter 4.1, which was the central processing unit. Next on, we'll move on to system buses in the next video. Thank you.